Hello and welcome to this A-level chemistry explanation video where we're going to be taking a look at the first part of the thermodynamics topic, looking at some enthalpy change definitions, enthalpy of solution, lattice enthalpy, and Born-Haber cycles. Entropy and Gibbs free energy will be a separate video that you can check out after this. There are lots of different enthalpy change values that you need to be able to define and to understand and apply in the thermodynamics topic, and therefore a quick recap of what enthalpy changes are would be really useful. So first of all, enthalpy changes generally are the heat energy transferred in a chemical reaction at constant pressure. The units for this enthalpy change are usually reported in kilojoules per mole, and to save time, we normally write delta H for the change in enthalpy. We also normally write a little circle with a horizontal line through, and this is to denote that the reaction has been taken place under standard conditions, and so this is often referred to as the standard enthalpy change. Standard conditions are for things such as temperature, which is 298 Kelvin, pressure, which is 100 kilopascals, which is just under 1 atmosphere of pressure, and for solutions, we're talking about solutions which have a concentration of 1 mole per decimeter cubed. The values for enthalpy changes can be exothermic or endothermic. In an exothermic reaction, the enthalpy change has a negative value, and that's because chemical energy from the reactants has been converted into thermal energy from the surroundings. And so from the point of view of the reactants, the chemicals, they have lost energy. That chemical energy is converted into thermal energy, and so the temperature goes up. Endothermic changes are the opposite. They have a positive enthalpy change value, and that's because the chemicals have gained energy. Where does it come from? It comes from thermal energy of the surroundings. And so thermal energy is converted into chemical energy, and so that means there is less thermal energy than there was before, and therefore the temperature will decrease. The most important enthalpy change in the whole of the thermodynamics topic is something called lattice enthalpy. Lattice enthalpy is to do with ionic compounds, and this makes sense because ionic compounds exist as a three-dimensional lattice. You can see from the diagram that I've got here that we've got positive ions next to negative ions in an alternating pattern. I'm showing 9 ions here as one plane. This would of course go off into the distance in these two directions and then off into the distance in the third dimension as well. These ions are held together by very strong electrostatic attractions in all directions, and this is what ionic bonding is. And you can see this positive ion in the middle here has got 4 oppositely charged ions that it will be attracted to that we can see. There will be another one going into the screen and a 6th coming out of the screen. Why does lattice enthalpy matter? Well, it influences a number of things, as we shall see. Just to give you a few examples, we have got boiling point. That is heavily influenced by the lattice enthalpy of an ionic compound, as is the solubility of that compound, and to an extent, the reactivity of that compound is also influenced by the lattice enthalpy as well. There are actually 2 different types of lattice enthalpy. There is firstly the lattice formation enthalpy, and that is defined as the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions. And if we assume that these red and blue circles are the positive and negative ions, you can see that if we turn these into a solid, what we're doing is we're bringing them back into the more regular lattice arrangement that we had on the previous slide. And you can see that they were randomly organized and now they are in that lattice structure. And so that is the lattice formation enthalpy. And you can write this as an equation. So for instance, if we take sodium chloride as probably the most common example, at the beginning we had gaseous sodium ions and gaseous chloride ions. They were singly positive and singly negative. And then once they've come together to make their ionic compound, we have got NaCl solid. Since we are making new attractions, this is the ionic bond, this will be an exothermic reaction because energy is always released when new attractions are being formed. The other type of lattice enthalpy is the lattice dissociation enthalpy, and this is actually the precise opposite of lattice formation enthalpy. So it is defined as being the enthalpy change when 1 mole of solid ionic compound is completely dissociated into its gaseous ions. And so if I just take my solid ionic lattice as I've got it here and I dissociate this, I'm pulling the ions away. Now, to do this, this will require energy because these ions are held together by those strong electrostatic attractions. And so this is always going to be endothermic because I'm overcoming the force of attraction between the positive and the negative ion, and that will require energy to go in to make that happen and to break apart these ions into the gas form. Just like lattice formation enthalpy, we can also represent this as a chemical equation. It is in fact the exact opposite of the previous example. We're starting with our ionic solid, NaClS, and we're making our positive and negative gaseous ions, so the sodium plus and the chloride minus. And so lattice dissociation enthalpy is the precise opposite of lattice formation enthalpy. And so that means that the lattice formation enthalpy is negative. In this example with NaCl, it's minus 787. And the lattice dissociation enthalpy is going to be plus 787. So they are equal in magnitude but opposite in sign, because one of them releases heat energy to the surroundings, whereas the other one takes heat energy in and converts it into chemical energy. It's a common command in A-level exam questions to compare the lattice enthalpies for two different ionic compounds. And the value for a lattice enthalpy depends on the strength of the attraction between the positive and the negative ions. And these electrostatic attractions depend on the size of the ions and the magnitude of the charge on the ions. And these are often rolled into one term, which is referred to as the charge density. And that is quite literal. It is how concentrated the charge of a particular ion is. If we look at a couple of examples and say compare NaCl to KCl. In an exam situation, they usually do try to keep one of the ions being the same because that allows you to ignore that from our consideration. So I'm just drawing a single circle for the Cl- that will be the same in both examples. Sodium is higher up group 1 than potassium, and so it will be a smaller ion, or it will have a smaller ionic radius. And therefore, its charge is more concentrated because both of them are singly positive ions. And so you could say that the sodium has a higher charge density as an ion than the potassium. As a result, the electrostatic attractions will be stronger in NaCl than it is in KCl, and so the lattice enthalpy will be more exothermic. And that's really important, that clarity of language, that we should avoid saying larger or smaller because lattice formation enthalpies are all negative values. I would encourage you to say more negative or more exothermic. Or if it's a dissociation enthalpy, you could say more positive or more endothermic. If we look at adding magnesium chloride into the consideration, magnesium is doubly positive, and so that 2+ ion is likely to have a higher charge density than the Na+ and the K+. And additionally, magnesium is significantly smaller than sodium even, which was the smaller of the two singly positive ions. So magnesium chloride would definitely have a more exothermic or a more negative lattice formation enthalpy. One final pairing, if we compared MgCl2 to MgO, this time the positive ions are both the same, so any differences will not be down to that ion. It will be down to do with the size of the Cl- ions charge density and the O2- charge density. And so you'd expect the O2 minus to both have a smaller radius and also to be more highly charged. And so therefore it will have a higher charge density and a more exothermic lattice formation enthalpy. I'm now going to take a look at how the strength of an ionic lattice can affect that compound's solubility. In order to dissolve an ionic compound, energy needs to go in to break apart that lattice, and this is the lattice dissociation enthalpy. As I've already said, dissociation is an endothermic process because we need to overcome the attractions between this positive and negative ion in all of those 6 different directions. Where does this energy actually come from? Well, it comes from the water, the solvent that is going to do the dissolving. This works because the water solvent forms new attractions to the ions in the lattice, and this creates an aqueous solution. In this aqueous solution, we say that the ions have been dissolved until we have got infinite dilution. And what that means is that there is no electrostatic attraction between the positive and the negative ion anymore. Those attractions are purely between the ions and the water solvent. And this works because water is a polar solvent. Some regions of the water are delta minus, specifically the oxygen atom, and some are delta positive, and that will be the hydrogen atoms. And so what we get is the delta positive hydrogen atoms in the water molecule are attracted to the negative ion from whatever the ionic compound was. And similarly, the oxygen atom from the water molecule will be attracted to the positive ion from the ionic compound. And these form new attractions. And this process of forming new attractions between the gaseous ions and the water solvent to make the aqueous ions is called the enthalpy change of hydration, or the hydration enthalpy. Since we're making new attractions, these processes are always going to be exothermic, irrespective of what the charge of the ion is. We are always making new attractions between one region of the water and the ion itself. In an exam situation, you might be asked to comment on the exothermicity of the enthalpy of hydration, which is not as complicated as it sounds. The charge density of the positive ion, for instance, will affect the strength of its attraction to the delta minus oxygen in the water. So, for instance, Mg2 plus or Na1 plus, the Mg2 plus will have a stronger attraction to the delta minus oxygen because it has a higher charge density. And this works exactly the same for the negative ion, except the attraction is to the delta positive hydrogen. And this can have such a huge difference to the enthalpy of hydration, but not only that, the number of water molecules that can actually cram in around the positive or the negative ion, to the point where some highly charged small ions, such as aluminium 3+, for instance, can have a huge number of water molecules forming ring upon ring of water molecules around it. You don't need to memorize any of these specific examples, but you do need to be able to comment on charge density and speculate as to whether that will lead to a more exothermic enthalpy of hydration or less. The precise value for the enthalpy of solution, and so whether it is an exothermic process or endothermic process, depends on the balance between this lattice dissociation enthalpy and the hydration enthalpies. If the magnitude of the hydration enthalpies is greater than the lattice dissociation enthalpy, it will be an exothermic enthalpy of solution. If not, then it will be endothermic. We can use a Hess cycle and Hess's law to work out a value for the enthalpy change of solution for an ionic compound. Hess's law states that the enthalpy change for a reaction is independent of the route taken for that reaction. It depends only on the initial and final energies of the chemicals. If we take a look at the 3 equations that we need for a Hess cycle here, we've got the enthalpy of solution equation, And in general, this is where you start with 1 mole of an ionic solid and you make that into aqueous ions. If we go for an example, sodium chloride, the most common example, we start with NaCl solid and we end up with Na plus aqueous and Cl minus aqueous, which is sometimes okay to write as NaCl aqueous in one form, but I tend to separate those out. And then if we look at the lattice dissociation enthalpy, the definition there is 1 mole of an ionic compound in solid form turns into its gaseous ions. And so NaCl(S) turns into Na plus gaseous and Cl minus gaseous. And last of all, this new term of the enthalpy of hydration. This is where you've got the gaseous ions, so Na plus G turns into aqueous ions, so Na plus aqueous. And the same thing for the chloride ions. And you can take these enthalpies of hydration separately, or you can hydrate them both simultaneously, but the enthalpy change for this reaction will be the sum of the individual hydration enthalpies. Now, if we construct these into a simple Hess cycle, you can see that we can make a triangle. Hess cycles are typically triangles, and they're made up of overlapping equations. And what I mean by that is each vertex of the triangle is formed where two equations overlap and say the reactants are the same for those two equations. And so if we take the enthalpy of solution, we've got the ionic solid at the beginning, and that's the same for the lattice dissociation enthalpy. So an ionic solid forms one corner of the triangle. However, the equations go in different directions because one of them turns into the aqueous ions and the other turns into the gaseous ions. And then the hydration enthalpy is when gaseous ions turn into aqueous ions. So this arrow of the triangle is referred to as the sum of the hydration enthalpies. And we can use this template for sodium chloride. We start with NaCl solid in one corner, we turn it into Na plus and Cl minus aqueous along the top, and Na plus and Cl minus gas down at the bottom corner. And then the Na plus gas arrow goes up to the Na plus aqueous, and the Cl minus is all part of the same arrow. And it's this arrow that you could separate out into two separate steps if you wished. And then you can use this Hess cycle that we have constructed to work out what the enthalpy change of solution will be. And so you can see that the enthalpy change of solution is along the top, and that is equal to the lattice dissociation enthalpy plus the sum of the hydration enthalpies. And so for sodium chloride, the lattice dissociation enthalpy is plus 787 kilojoules per mole. And the hydration enthalpy of sodium is minus 406 kilojoules per mole, and for chloride it is minus 364. So the enthalpy of hydration in total is minus 770. And so we can say that our enthalpy of solution is plus 787 plus minus 770, and that gives us plus 17 kilojoules per mole. And so that means that the enthalpy change of solution for sodium chloride is a slightly endothermic value. There is a second type of enthalpy change cycle that you need to know about in the thermodynamics topic, and this is called the Born-Haber cycle, named after two German scientists, Max Born and Fritz Haber, and that's the same Haber who devised the Haber process. Born-Haber cycles work in exactly the same way as Hess cycles, which is that you can use them to work out an unknown enthalpy change value, but also the enthalpy change is still independent of root. It doesn't matter if you're using a Hess cycle or a Born-Haber cycle. There are two main differences between Born-Haber cycles and Hess cycles, and the first is one of shape. Born-Haber cycles are rectangular in shape, which seems a little bit odd. But what this ends up meaning is that the chemical equations are written at 90 degrees to the angle that you would expect them to be written at. And so the dissolving of sodium chloride is something that we would typically see written like this. But if it was in a Born-Haber cycle, we would write it at 90 degrees. The reactants, sodium chloride solid, would then point upwards to the sodium ions and chloride ions in their aqueous state. So that's the first difference. The second difference is that we actually have a y-axis to these cycles, and that y-axis is energy. And the significance of this is that the direction that your arrow points in a Born-Haber cycle tells you if this reaction is exothermic or endothermic. In other words, do the chemicals end up with more energy at the end of the reaction, endothermic, or less, which would be exothermic? And so for my example that I've drawn here, this is an endothermic process because the chemicals are gaining in energy and there will be a temperature decrease. And so we can construct a full Born-Haber cycle for the dissolving of sodium chloride like so. The sodium chloride solid can turn into gaseous positive and negative ions. That's a regular equation, as I've written here. But since this is going to be significantly endothermic, plus 787, as discussed previously, then this is going to be a large endothermic arrow going quite a long way up on the cycle. And we've got the gaseous ions along the top, which can be hydrated, which means they can become aqueous ions, and this is going to be exothermic because new attractions are being formed. Once we've got this cycle, we use it in the exact same way as using a Hess cycle, and so you can see we've got plus 787, and that then is added to minus 770 to give us our enthalpy change of plus 17, which is, of course, the exact same number we got from using the Hess cycle. And you can use this for any of the unknown 3 values in a Born-Haber cycle. It doesn't always have to be the enthalpy of solution that you're calculating. And the most tricky example might be if they gave you the enthalpy of solution, they gave you the lattice dissociation enthalpy, and they gave you one of the hydration enthalpies, and you had to treat this hydration enthalpy arrow as being equal to the enthalpy of hydration of sodium, which, say, we didn't know, plus the enthalpy of hydration of chloride, which we did know as minus 364. And so we'd have this arrow being plus 17, this arrow being plus 787, and this arrow being x plus minus 364, which we could then rearrange and solve that for obviously getting us the answer that we know it should be of minus 406. We can calculate a value for the lattice enthalpy using the electric field strength equation that you might encounter in physics, but it's not something that you can measure directly. In order to determine a value for the enthalpy change of lattice formation or dissociation via an experiment, you have to do this indirectly through a series of other different enthalpy change experiments and combine them together in a Born-Haber cycle. You will have encountered these enthalpy changes earlier in A-level chemistry. For instance, the enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. Now, in the thermodynamics topic, you're going to be making an ionic compound, but it doesn't have to be for the enthalpy change of formation by definition. And so, for instance, if you had magnesium chloride, you'd have solid magnesium and then Cl2 in the gas form, and you'd make MgCl2 in the solid form. If we had NaCl, this would be a little bit different because you have to, by definition, make 1 mole of an ionic compound. And that means there has to be a 1 in front of the NaCl, which means you only need 1 mole of chlorine atoms, which means you only need half a mole of chlorine gas molecules. In the atomic structure topic, you first encounter the ionization energy concept. And this is the energy change when 1 mole of gaseous singly positive ions, or 1 plus ions, are formed from 1 mole of gaseous atoms. And so to stick with the elements that I've already been looking at, we've got Mg gas turns into Mg1 plus gas plus an electron. It's absolutely essential to include that electron that has been lost. Or for sodium, we've got the same thing, but we've just changed the magnesium symbol for sodium. We can also ionize some things more than once. And this is the enthalpy change when 1 mole of 2 plus gaseous ions are formed from 1 mole of 1 plus gaseous ions. And we can write this as an equation as well in this form, exactly in the same way as previously, except we can see that we're starting with 1 plus ions and finishing with 2 plus ions and that electron. Ionization is always an endothermic process, since we're having to overcome the electrostatic attraction between the nucleus of the atom and that outer electron that is being removed, and that always requires energy. And the second ionization energy is always going to be larger than the first ionization energy. Electron affinity is effectively the opposite of ionization energy for a couple of reasons. First of all, by definition, it is the enthalpy change when 1 mole of gaseous 1- ions are made from 1 mole of gaseous atoms. This means we might be starting with 1 mole of single gaseous oxygen atoms. They're going to gain an electron and we're going to make O- gas. Or we might have chlorine gas plus an electron making Cl- gas. Both of these are making new attractions between the atom and the electron that is being gained, and therefore this is going to be an exothermic process because a new attraction is being formed. The exception to this is the second electron affinity. This is the enthalpy change when 1 mole of gaseous 2- ions are made from 1 mole of gaseous 1- ions. You can see again I'm using oxygen as my example. This time the oxide 1- ion is gaining an electron to become the oxide 2- ion. This will actually be an endothermic process even though we are making a new attraction. And the reason for this is we are having to overcome the repulsion between the negative electron and the negative O- ion that is gaining it. And overall, energy has to go in to make this reaction happen. Enthalpy change of atomization is defined for an element as the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state. And so that might be sodium, for instance. Na solid turns into Na gas. We might say it has been atomized. This, by the way, is in this instance the same process as sublimation. Alternatively, we might make 1 mole of gaseous chlorine atoms. And for that to be the case, we would have to atomize half a mole of Cl2, because in order to produce 1 mole of chlorine atoms, we would actually need half as many chlorine molecules because they are diatomic. If we broke apart a full mole's worth of Cl2 to make 2 moles of Cl gas, this would actually be the bond dissociation enthalpy. So that's the enthalpy change when all the bonds of the same type in 1 mole of gaseous molecules are broken. So in this instance, the Cl to Cl covalent bond. And the relationship between bond dissociation enthalpy for a diatomic molecule and atomization is that bond dissociation will be precisely double the atomization. And these are always endothermic because energy is going in to break those bonds. And so the bond dissociation enthalpy for chlorine, for instance, might be 242 kilojoules per mole. And that means that the enthalpy change of atomization of chlorine will be 121 kilojoules per mole, exactly half, because what you're doing is you're breaking half a mole's worth of Cl to Cl bonds instead of breaking a whole mole of Cl to Cl bonds. A definition of atomization that you encounter far less frequently is if you are atomizing a compound, and that is when you take 1 mole of a compound in its standard states and you convert that into gaseous atoms. For an organic molecule, such as methane, this will involve the breaking of 4 carbon to hydrogen bonds. So the atomization of methane is going to be 4 of the bond dissociation enthalpies of carbon to hydrogen. But if we had an ionic compound, for instance sodium chloride, the process would be turning 1 mole of sodium chloride solid into 1 mole of sodium gas and 1 mole of chlorine gas. We're now going to take a look at how you can use a Born-Haber cycle to work out one of the enthalpy changes that we've just been discussing. I'm going to use sodium chloride as my example again, but I'm also going to try to generalize at the same time. First of all, it's important to begin with the end in mind. We are working with an ionic compound, and so sodium chloride is our ionic compound, and that will be on the bottom of our cycle. We can make sodium chloride in two different ways. We can make it from its elements in the enthalpy of formation, and this is going to be enthalpy change number 1 that I'm going to write on the bottom left. Alternatively, we can make it from its gaseous ions, and that's going to be the arrow on the right-hand side. And this is the lattice formation enthalpy for sodium chloride. Both of the arrows are pointing down towards the NaCl solid, implying that this is going to be exothermic. You're not actually expected to memorize whether or not sodium chloride would have a negative enthalpy of formation or not, but you are absolutely expected to know that it would have a negative lattice formation enthalpy. And then what we need to think about for the rest of our cycle, and the way that I recommend that you remember how to construct these, is how can we get from the elements sodium and chlorine on the left-hand side round to the gaseous sodium ions and the gaseous chloride ions? Well, the answer is sequentially, one substance at a time, we need to convert them and work towards them becoming ions. So for instance, we've got sodium solid at first. We need to atomize it. And so this first arrow that's going to be pointing upwards is the atomization of sodium, and it's going to be endothermic. Energy has to go in. One of the rules for these arrows on the cycle that I'm going to use to connect my elements with my gaseous ions is that you only change one substance at a time. So while the sodium has been atomized, the chlorine is unchanged. So we just write half a Cl2G again. Now we deal with the chlorine, we're going to atomize the chlorine, and this is going to produce Cl gas. And this means that the sodium is untouched by this process. And so this arrow, which I'm labeling as enthalpy change number 3, is the enthalpy of atomization of chlorine. The sodium is unchanged. Now, a quick check over onto the right-hand side reminds us that we've got sodium ions. And so our next arrow is going to be to ionize that gaseous sodium and turn it into a positive ion. And so this is enthalpy change number 4. That is the first ionization energy of sodium. And so as a result of that change, the gas sodium has turned into the sodium plus gas, so the ion, and as a result, it has lost an electron. And so we need to include that electron in the cycle. And the chlorine is untouched. It is still the gas. And the final step to complete our cycle is to convert that chlorine, which is a gas, into the chloride ion. And so it gains that electron that the sodium has just lost. And so the sodium ion is completely unchanged, but the chlorine goes from being a gas to a negative ion. And that is the electron affinity of chlorine. Now we've constructed our Born-Haber cycle. I know it looks much more complicated than a Hess cycle, but how we use it is exactly the same. So suppose we wanted to calculate this enthalpy of formation, so delta H number 1. That means that we're starting at the base of this arrow and we're going to the head of the arrow. And remember the rule of Hess's law, it's that it doesn't matter where you start and finish, the enthalpy change will be the same. So that means that this enthalpy change arrow number 1 will be the equivalent of going with enthalpy change number 2 and enthalpy change number 3 and enthalpy change 4 and enthalpy change 5 and enthalpy change 6. So using this Born-Haber cycle, we can see that the enthalpy of formation is actually equivalent to the sum of all of those 5 other enthalpy change arrows, provided the lattice enthalpy is lattice formation enthalpy. Equally, we could calculate any of those other values. We could calculate the lattice enthalpy itself, which really is why the Born-Haber cycles are used, but in an exam situation, it doesn't have to be. And so enthalpy change number 6 is going to be starting at the base of that arrow and going to the bottom. And if we work our way around this cycle anti-clockwise, you can see that we are going against 4 of these arrows, and so the sign would flip over. And so enthalpy change number 6 is equal to enthalpy change number 1 minus enthalpy change 2 and 3 and 4 and 5 that have all been added together. As a general rule then for Born-Haber cycles, you have your ionic lattice at the bottom, you have the elements in their standard states above that and to the left with an arrow connecting the two. You've got the gaseous ions probably above that and to the right, and then you've got one of the elements has been atomized, and then the other element has been atomized, so that's 2 atomizations, one after the other. Then we ionize the metal gas atom, and then the non-metal gas gains that electron that the metal has just lost, and this completes the cycle. Don't forget the electrons need to be included at the top of this cycle. If we take a look now at a more complicated Born-Haber cycle for an ionic compound that raises a couple of different issues. The way that we need to construct the cycle is exactly the same though. So you start by putting the Na2O solid down on the bottom line. The elements that make that up will be 2 Na solid plus half an O2 gas. And we are going to be making this ionic lattice ultimately from 2 sodium 1 plus gas ions and 1 O2 minus gas ion. And so this is 3 of our steps completed. The cycle continues in a similar way to the previous cycle. We need to atomize our solid sodium. And so we're going to end up turning our 2 sodium solid into 2 sodium gas. And so this means that this arrow that I've just drawn is not the enthalpy change of atomization of sodium. It is 2 times by the enthalpy change of atomization of sodium, because I needed to put that energy in twice to atomize both the moles of sodium solid. And then we're going to atomize the oxygen, which is going to produce O gas, 1 mole of it at the end, and the sodium is unchanged by this second upwards arrow. If the question was being confusing, it might not give us enthalpy change of atomization for oxygen, remember, it might give us the bond dissociation enthalpy, and in that case we would have to halve it. The next step is we need to ionize our sodium, and so not only are we ionizing 1 mole of sodium, there are 2 moles of sodium gas that needs to be ionized. So this arrow is 2 times by the ionization energy for sodium. As a result, we make 2 sodium 1 plus gas ions, and we produce 2 electrons, 1 from each of those sodium gas atoms that has been ionized. And so our oxygen is still a single gas atom, and we've now got our gaseous sodium ions. The oxygen needs to be gaining those electrons one after the other. The first electron affinity is where 1 of those electrons has been gained, and that will be exothermic as normal. The second electron affinity is where the O1 minus gas ion gains the electron, the 1 electron that there was left over, that needs to be included still. And then it becomes an O2 minus ion, which is a gas. And so we've now got our gaseous ions on the top right. Remember, this arrow is pointing upwards because it is an endothermic process, because energy needs to be put in to overcome the repulsion between the O minus ion and the electron that is being gained. So they are both the same negative charge. Using this Born-Haber cycle is exactly the same as for sodium chloride. The exception is that any enthalpy change that is to do with sodium and not the oxygen would need to be doubled, because we need to atomize 2 sodiums and we need to ionize 2 sodiums. And if they were being mean and they were asking you to work out from this Born-Haber cycle what the enthalpy of atomization of sodium was, you would do this in the exact same way that you would expect. So enthalpy change number 2, for instance, And so this enthalpy change of atomization arrow that I'm putting the little star next to, starting from the base of that arrow and going to its head, is the same as going this anti-clockwise journey around the cycle. And so in other words, the enthalpy of formation minus the lattice enthalpy of formation minus the second electron affinity minus the first electron affinity minus the ionization times by 2 minus the atomization of the oxygen, all of those are equivalent to 2 times the atomization of sodium. So that means that when you calculate those numbers and you get your value, you then need to divide that by 2, and that will get you your atomization of 1 mole of sodium. The completed Born-Haber cycle for calcium sulfide looks like this. You can see that we've got 8 arrows this time. That makes it look pretty complicated, but it still follows the typical Born-Haber cycle format. We've got the ionic compound at the bottom, 1 mole. We've got the elements on the line above and to the left, and we've got the gaseous ions at the top and right. Everything looks normal so far. We've got the atomization of calcium, so step 1. Atomization of sulfur is a separate second step. And then we've got the first ionization energy for calcium. Don't forget to include the electron that has just been lost when the calcium forms the gaseous positive ions. And then the second ionization energy of calcium. So this time we're making 2 electrons. We had 1 already. The second electron has now been lost. And so we've got calcium as a 2+ ion. And all the while this sulfur is unchanged. And so this is the new arrow. Then we've got the first electron affinity of sulfur. Remember, it's exothermic because a new attraction is being formed. And then the second electron affinity for sulfur, endothermic because we're overcoming the repulsion between those 2 negative substances. And then we've got the lattice formation enthalpy on the right-hand side. And so the typical 6 arrows have been joined by the second ionization and the second electron affinity. But how we use the Born-Haber cycle is exactly the same. Let's suppose we were working out this enthalpy of formation. It is still equal to, when you follow all of these arrows, they're all going the same direction. And so the enthalpy of formation is still equal to the sum of all of the other arrows. The ions in an ionic compound, in that lattice, are held together by electrostatic attractions, which are very strong and they require a lot of energy to break. You can actually calculate the strength of this electrostatic attraction using the electric field strength equation that you might know from physics, and so that means that you can calculate a theoretical value for a lattice formation enthalpy. When we consider lattice enthalpies like this is referred to as the purely ionic model or the perfectly ionic model. And this makes one really big assumption, which is that ions are perfectly spherical, which when we do the maths is an essential assumption, but when we do the experiments, we find out that it is not the case. And the reason for this is that the positive and the negative ions do not exist as isolated perfect spheres. In reality, what happens is the electron clouds around each of these ions get distorted or polarized by attraction from the other ions. Now, the good news is for A-level chemistry, they allow you to isolate this as an effect on the negative ion. And so we always talk about polarization of the negative ion by the positive ion. But in practice, it would in fact go in both directions. And it follows that the charge density of the positive ion is going to have a really big influence on how much polarization occurs of the negative ion. For instance, a small, highly charged positive ion will be highly polarizing, whereas a large, singly negative ion will be highly polarizable. And so as a result, you can get significant differences in polarization of the electron cloud around the negative ion. For instance, aluminium chloride would have significantly more polarization than lithium chloride because aluminium is a 3+ ion. The polarized negative ion leads to there being electron density between these two ions. So we've still got the positive ion attracting the negative ion, but we've got some electron density in between them as well. And that's what a covalent bond is. It's some electrons between two nuclei, and the nuclei are held together by a mutual attraction for those electrons. And that's what a covalent bond is. And so this ionic substance has actually got some covalent character in addition to the electrostatic attraction that is unchanged by this polarization. And this leads to the lattice being stronger than you might expect, and so the lattice formation enthalpy would be more exothermic than you would expect it to be. A good way to explain the purely ionic model is to compare it to the purely covalent model. And in fact, the purely covalent model is easier to understand because we know that in covalent substances, the electronegativity difference can lead to a polar bond or a non-polar bond. And the best way of saying something might be purely covalent is if we had a diatomic molecule that was an element. So hydrogen, oxygen, nitrogen, fluorine, etc. This will be purely covalent because there is no electronegativity difference between the atoms that are sharing that pair of electrons in the covalent bond. We know that you do sometimes get an electronegativity difference though. For instance, in hydrogen chloride, you end up with a polar covalent bond because the hydrogen is electron deficient because the chlorine has pulled the electrons away towards itself, and we've got this polar bond forming because the chlorine is more electronegative. And so this is a covalent substance with some polar nature. For a perfectly or a purely ionic substance, you need to have perfectly spherical ions with no polarization. And the best way of getting this is if you've got a low charge density positive ion, in other words, it's not very polarizing, something like potassium that is big and singly positive, and a very small singly negative ion, so it's not very polarizable. So a good example might be potassium fluoride. There would be very little additional covalent character because there would be very little polarization at all. Whereas as you get something such as magnesium oxide, which has got a positive 2 ion, it would be quite polarizing, and so there would be some polarization and some additional covalent character. And so we've got a continuum with purely ionic and purely covalent at the ends, and not many substances actually existing at either end. And you've got most substances being somewhere in the middle, being either ionic or covalent, but having something of the nature of the other. In an exam situation, you might be asked to consider the difference between the theoretical and the experimental lattice enthalpy values, and this could take a number of different forms. For instance, which would you expect to have the largest difference between theory and experiment, sodium bromide or magnesium bromide? Now, in both of these examples, the negative ion is the same. That means the bromide ion is going to be equally polarizable in each instance. And so the difference comes down to the positive ion. The sodium is 1+ and larger than the magnesium, which is 2+. And so therefore the charge density will be greater on the magnesium ion. So there will be more polarization of the bromide ion in magnesium bromide. And as a result of that, there will be more of a difference between experiment and theory, and there will be more additional covalent character in magnesium bromide. Alternatively, they might ask you to compare two values that you have been given. So for instance, sodium chloride, its theoretical lattice enthalpy is -766 and its experimental value is -787. in this instance, these values are really quite close together. And so since the values are close together, you can say that there is very little polarization of the negative ion, and so therefore there is very little additional covalent character in sodium chloride. And that's likely to be because the chloride ion is quite little and not very polarizable, and the sodium ion similarly is not very polarizing. Or they might give you an example where there might be a big difference. So for instance, magnesium iodide, where you've got -1944 for the theoretical value, but the real lattice enthalpy is much more exothermic because it's -2327. And so in this case, you would be saying that there is significant polarization of the negative ion, which leads to significant additional covalent character, and therefore the lattice is much stronger than you would expect. We've got a much more exothermic value. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.